Yes, it's recording.
All right, thank you.
Okay, perfect. Okay, so sorry, I missed it. I don't know if Dawn introduced me, but I'm Colonel Stephen Hamilton. I'm cyber. I used to be a signal officer. I got converted to a 53, which is an information systems automation officer a while back, and then I eventually converted to cyber as I set up the cyber branch in the Army. So this will be a fun story since you guys know Dawn. I got to ACI, the Army Cyber Institute, in 2017 in the summer. I was buying the house that I'm sitting in right now. Well, actually, I was trying to buy a different house, I think. New York, buying a house is not something I'd recommend to anyone on the planet. But I eventually moved into this house that I'm in. But during that time, I was actually in a, we were staying in a camper. And I came in one day to Don, and he was like, "Oh yeah," he's like, "Yeah, we're one of the things we're looking at doing at ACI is looking at HF radio." And I was just like, "What?" I was like, "Why is that?" And he's like, "Oh yeah," he's like, "Well, because the Army's concerned that when satellites go down due to cyber incidents, then the only long haul communications that exist is really HF radio." And as soon as he said that, I was like, oh, of course, but also, wait a minute, like really, like, wait a minute, what's going on here? And so we sat down and had this discussion. And I was like, actually in my car, I have my my Kenwood TS440 sitting in my car because I'm moving, and I didn't want the movers to mess with it because I felt like if the apocalypse happens while I'm moving, I need an HF radio. Don almost lost his mind, and he's like, "Why don't you bring it in here?" I was like, "Yeah, I'll bring it in here. I'd be happy to set it up and start working on it." Well, this is in 2017. If you think about the timeline of that, FT8 was coming out during that time. So I'm taking this 1985 radio, setting it up. I bought a signal link, and then we got it up and running on FT8. And I realized that, I mean, that literally, I didn't realize it at the time. I look back, and that's the tipping point of HF is getting a renaissance right now in the military. And Don was on top of it. He was talking about it before I got there. I was just happy to do stuff that I do as a hobby at my work. That was the most amazing thing. So that's the beginning of this kind of journey that I've had since I got to the Army Cyber Institute. So the picture here that we have here is Spelman Hall, which is there's some interesting history behind this, but it's basically, it used to be Lady Cliff College, which was I think kind of folded in like 1980. It was a women's college up until like 1978, and then they admitted men for the last 2 years. And then West Point bought the property. The West Point Museum is actually the main school area that you see in the middle, and off to the right is the dorm area from the old Lady Cliff College. It's been renovated, and the reason why I was in a trailer with a temporary trailer with Don is they were renovating this for the top 3 floors are ACI, and the bottom 3 floors are for the Network Enterprise Center, and also the G6. And so some of our actual circuits for West Point actually come in through this building. So it's kind of it's a strategic building when it comes to comms. But in any case, that's the picture there. So just to give you a quick idea of how cyber works in the Army, I'm in the top left corner of these 51 personnel. We're a research institute that looks like 10 to 20 years out, 5 to 10 years out, depending on who you talk to in ACI. People are looking at everything literally from 0 to 20 years out of what are strategic problems that we need to work on that the Army doesn't have time to look at. So if you look on the right-hand side, I just talked to many people here in a conference call earlier today in our cyber, and they're fighting the day-to-day fight. So they're the frontline people fighting on the cyber side, defending our networks, and also doing things to prevent us from getting attacked in the future on the offensive side. So they are the biggest component. They're the working component. And then you also have down here Fort Gordon, Georgia on the bottom of this, which is, I don't know if you can see my mouse or not, but at the bottom triangle is what I'm talking about, which is the Fort Gordon Cyber Center of Excellence, which is basically, if anybody here's served in the military, been in the military, it's where you do your AIT, OBC, BOLC, whatever acronym you want to call it. It's where the basic training goes for people going into the cyber force, officers and enlisted, and also it's also the Signal Center happens to be there as well. So the Signal Center of Excellence is also in the same place. So that's kind of how we lie out in these things. We're just kind of a small piece, but we're separate from the two major entities of cyber, which is why I'd like to kind of show the slides to give people an understanding of why we do things that are kind of on the, I hate to call it the fringe, but we're a little bit on the fringe of what the rest of the Army's doing. So if I say something that sounds like the Army's, why are the Army doing this? We're not like the traditional force. The U.S. Army Cyber Command is doing stuff, and a lot of that stuff is probably classified anyway. I will say that at Fort Gordon, and our cyber has actually just recently moved from Fort Belvoir, Virginia to Fort Gordon in the last, I guess, last year. They have some, they're extremely talented people. And the interesting thing is the Signal Center had their Mars station went defunct. If anybody works with Mars, we may have some Mars operators here. But one of the guys that used to work with us at West Point, not in ACI, but he was in the electrical engineering department. He has restood up a Mars, or he's restood up a Fort Gordon club, and standing up Mars and really kind of fixing what's kind of missing down there. So I say that because a lot of this I think about is I mean, to be honest, what's happened with the Army in the last 20 years is we kept fighting this war on terror, focusing on people who did, you know, sly things like IEDs and stuff with cell phones, but who traditionally didn't have like a big electronic warfare component, and also not a big HF component. And so a lot of people think that HF is kind of Cold War comms. And really what it is, it's comms that's separate from satellite comms. We just got so happy with our satellite comms that because we could fight the war on terror with it, then we were happy with it. And during that 20-year period, there's been some training and educational atrophy that's happened. So that's kind of the gist of this. So where is HF in the Army? Real quick, just to go through this, we have all three of these radios at the ACI. I'm pretty happy about that. Actually, we don't have the 138s right now. They're sitting at Harris getting refurbished right now. The PRC 150 is our HF radio that's kind of the standard across the Army. It does 2G and 3G ALE. And so I think one of my slides talks about this. I need to, if anybody hasn't done ALE, it's automatic link establishment. It's basically dumbing down how HF radio works for soldiers. So it's actually a brilliant idea that actually works pretty well. It's interesting. The one thing I would say is that you have to realize that even having something that's so cool as an ALE radio that can automatically figure out what frequency and all of those kinds of things. I think we have somebody unmuted. Maybe I can mute. I don't know who. Okay, if I hear a ring or something, I'll mute it. But so the ALE concept is basically automatic link establishment. It is, as much as these radios may cost, it's a very basic process. It sends out a quick digital signal on a time sync, and it moves about every second or so. And it basically sends a signal out and tries to determine what's the best link quality between each radio. And then when you want to call a specific station, it can automatically select the best frequency based off of its last thing. So it's a brute force method. It's basically like taking vocab, throwing it out the window and saying, here, you know, if somebody has a good, again, I'll caveat it with, if somebody has a good mission plan and they know how to allocate frequencies, they can do things that which we all do as hams, right? We figure out, oh, well, 10 meters isn't good today, I'm going to go to 20, or 20 meters isn't good today, I'm going to do 40. Don and I have done this multiple times, trying to do NVIS shots between my house and his in Connecticut. I'm in New York, by the way. I guess this club is in Stamford, I guess, Connecticut. So the distance when you're in it, I guess the thing that's interesting is when you're a ham radio operator, you're just trying to either get something far or something unique when you're making a contact. And in the Army, what you want to do is talk to the person that you need to talk to. And so you don't necessarily know, you may know exactly where they're at, but you don't know exactly what's the best radio medium to get to them. And so ALE kind of solves a little bit of that problem by figuring out at least the best frequency to talk to them on. Okay, and then the PRC 160 is the, this one we just recently got 2 of these, and I would say it's a pretty badass radio. I'm pretty impressed with it. It is something that I would say, as a consumer, you're not going to buy something like this. We're talking in the 20K range probably for the price tag. So it's a little bit, I wouldn't call it over-engineered. You should be happy that the Army has taken your taxpayer dollars and bought some really solid HF radios that will perform. It performs extremely well. Okay, so there's that. All right, now we're going to go to NVIS. I feel like the more I talk about this, I feel like I'm either getting dumber or smarter or both at the same time. There's just a lot of confusion, I think, in the ham community about NVIS. And for the Army, it's an incredibly important thing, because if you think of a brigade, they're in kind of this 0 to 50 mile range when they operate, and getting communications between that works well on satellite. But let's say we're going against what we call near peer. So we're talking, I mean, to be honest, it's our potential adversaries of, just like Cold War, Russia and China. So if we're going against someone who has some significant technological capability, and they decide to jam our satellites, HF radio is a viable option for us to communicate. There's 2 pieces that I always say that comes with this is you have to realize your data rate's not going to be the same as a satellite, and you also have to, so you have to be able to command that way, which is its own piece. But you also have to realize how to do this. This is not, it's not hard, but it's really hard if you don't know how to do it. And it's funny because I had somebody at a ham play. It was a ham. It was before COVID. I went to a ham swap fest kind of thing, and someone was like, "Oh, you're doing NVIS. Like, what kind of specialized antenna do you need for that?" Well, a dipole isn't a specialized antenna. A dipole sitting at a quarter wave above the ground, configured properly, not really special, but it's a perfect NVIS antenna. So that's NVIS. I mean, it's what you're trying to do is go a very small distance, but still bounce off the ionosphere. I became more fascinated with this in the last few years because of our need in the Army to understand how it works. And it's funny to me that it's kind of still mystical to some people, which is fine. But when it becomes your job, you take it a lot more seriously. I remember as a ham as a kid, I just want to talk to, I remember talking to Germany on 10 meters and I was elated. I was like, this ham stuff is really, really cool, because I just talked to a guy in Germany. And so hams, I think, are a lot more focused on the DX contacts, which is, we have DX clusters, like we really push on that. Well, I think that the hams kind of forget about how propagation works when you're really going short range. And this is so amazing, as you'll see in a bit, when you start working through areas that has really rugged terrain. Even this area around here with mountains and stuff around, NVIS becomes like incredibly important. So I've read these crazy things that said NVIS only works 50 to 300 kilometers, and it's not true. I love to say, take that literature and just change your initial number to 0. You can shoot the signal straight up and straight back down, and I'll show you that in a minute. But it's definitely like possible to do that. So it's not like this, I hate to say it, but this concept of the skip zone, if you do a proper NVIS antenna, the skip zone doesn't exist for your NVIS comms. Okay. The last thing I'll put in here is from one of the more brilliant HF people back during the time, I think, when the Cold War kind of wound down, and we had, and I'm going to forget his name right now, and I feel bad that I am, retired lieutenant colonel, that he came and visited us not too long ago, but he wrote kind of a lot of the books on HF radio for the Army. But he was like, oh, if we just want to do NVIS, just tie the whip down on the vehicle, which as a ham operator, when I saw soldiers doing that for VHF, I was like, that makes no sense whatsoever. But for HF, there's some validity to doing this, because you want the signal to radiate directly upward, and you radiate perpendicular to the antenna, as you know. So it's a thing that I think is kind of important for people to understand, that you know, your antenna orientation is something that's going to matter when you're doing this. In the just pulling the antenna whip down to not hit a tree, for that functionality makes sense for like a VHF antenna. But for an HF, if you're trying to do NVIS, actually pulling it down, it enables you to do a form of communications that you normally would not think of doing. Okay, so all right, so I'll go very quickly on ALE. I already talked about this before, but all of us do this as hams, as a hobby, and it's always fun, is figure out, oh, I want to do this, I want to participate in this contest, I'm gonna make these little changes to talk on a frequency, or I'm going to get this big station that's operating out of Kuwait, something like that. You do that as a hobby, but when it comes to the Army, we have to do that as a purpose. Like, I need to talk to, you know, Unit A or Unit B. So when I need to do that, I need to do things right, which is these two basic things: frequency selection, antenna type, and height. And so if you can imagine, you know, taking the hobby aspect that you have of just trying to make different contacts and saying, no, I want to talk to, and maybe somebody's doing like work all state. So you want to talk to Rhode Island from where you're at. Well, you're going to have to do a NVIS shot, right? So it's going to be something that you're going to go up and come back down. You're not trying to hit like a large DX contact. So if you do that on a vertical from Connecticut, that may be a rough way to get there. That may not happen. Now, if you do it on a Yagi, much better probability, right? So, but these kinds of things are not something you want to be thinking about when you're in the field, and you know you're going to talk to someone, you know, X distance away. You just want it to kind of work, especially when you're talking about soldiers that they have other issues that they're trying to deal with, you know, while they're operating. So the idea behind ALE is super cool, because it basically says, I'm going to pick the right frequency to get to where I need to get to, and then it's going to save that data. And then when I key up, it's just going to automatically say, oh, you're talking to station 1. I'm going to pick what I have here, 5.25 megahertz. I do like this image because, and I would welcome any comments on this, but I spent a while trying to understand some of the concepts of the ionosphere. And as you go up in frequency, you start to penetrate through the ionosphere. As you go down in frequency, and I know it's maybe not real clear on here, I probably should redo it a little better, but as you go down in frequency, you start to absorb in the ionosphere. So your muff and your luff is determined by what's being absorbed or passed through or reflected. And the sweet spot is that reflection range. So the idea here is that we have our 5.25 megahertz happens to be in that sweet spot, and it comes down and gets that green kind of bar down to here. So anyway, I showed this to Army people. I know some of the hams here probably are just like, of course, this makes perfect sense, but visuals always help. So I wanted to point that out. All right, so antenna selection. And Don was there when we were in Nepal and we were trying to figure this out. And I tried to do a vertical and do a NVIS shot, and it was complete disaster. And our horizontal, big dipole worked perfectly. So the thing is, you obviously have engineering considerations. So what's portable? You know, what's going to fit on a vehicle? What's going to be something you could set up? How much time do you have to set it up? All of those kinds of things are just, we probably all know this as hams. You get comfortable, you build something at your house, and then you're like, okay, I could talk to so-and-so. This is a good antenna. But I would say I've become more and more interested in putting up a house vertical HF antenna, which is something that I wouldn't have thought of a long time ago. Because if I really want DX context, that's probably the better way to go. And if someone has any thoughts or comments on that, I'd like to talk to them, because I generally operate, once I get a nice antenna that works and I get a decent SWR, I'm pretty happy, because I'm not going to spend a whole lot of time operating, and I want to make it count. You know, the time that I am operating as a hobbyist, as a ham operator, as a for the military. I'm just trying to educate people on this at this rate. Okay, so with that, okay, so this is the cool part. So this is part that bends off of ham radio. So we have this system that Don was instrumental in when we started we started working on HF. He told me that there was an HF direction finding system, and I was like, wow, that would be super cool, especially for like contesting. I mean, it'd probably be cheating. I wouldn't use it for contesting, but I mean, it would be cool to use for contesting, I would say. But what if we could determine where a signal's coming from? And so this system that we have is something that was purchased by the government for specific targets in other countries. And basically the idea is it has 4 SDRs. I think I have probably, there's a lot of text on here. The basic system is it's 4 SDRs that pull in signals that are it's basically 4 cross dipoles and antennas that, or you could do 4 verticals, and it uses the SDR and looks at the phase difference between the signal as it hits the SDR in some kind of crazy math magic. And this is the part that I don't actually, I know it's possible, but because this works, but I can't explain the actual math behind it. But somehow the inventor of this, and he's a ham, figured out that if you look at the phase difference between each signal that comes in, you can tell the angle of arrival, which would make sense because it's going to hit one at a different phase than it's going to hit the other one, if you think about the actual radio frequency. But the real key to it is it can also tell you angle of elevation of arrival. And that part is a part that's still mind-boggling to me. However, it actually does this. So how that phase, I guess, I don't know if it's phase difference or what in the IQ. So there's the IQ data that comes out of the SDR, but there's a piece to it that he's been able to mathematically figure out how to calculate the angle that that it's arriving at. So if you have a NVIS shot, it's going to be coming down at a very high angle, like 85 degrees. And if you have obviously like a long a skywave shot, it's going to be coming at a much lower angle, maybe 40 degrees or something like that. And if you have a ground wave, it's going to be coming at 2 degrees or something. So that's literally the biggest thing that makes this system super cool. And we have a few of them at the Army Cyber Institute. So how does it work? It's got 4 HF front ends. So those are the 4 that I was talking about. And what those do is those actually do kind of the coarse DF. So they basically look at a huge amount of signal, but it's not, the resolution's obviously a lot less. And this is basically to find the signal of interest. So once you find the signal of interest, then you move into it's called a super DF. And then that's when your narrowband tuners start to refine where that signal is coming from. And this is the one that's going to give you that angle of arrival and elevation of arrival. And obviously they're all clocked together. They have to be if you're going to try to figure out the phase difference between, because it's just very, very, we're talking this thing's set up in I think it's 25 feet between each antenna or something like that. So, okay. So yeah, a little piece about this. It's IP based. So it basically what it does is it saves the the reality of this thing is it saves the IQ data in these FFT files. So it does the fast forward transform on it, save it in some files. And then once you do a super DF, you start recording all of that data, and it saves it in this polywave file. And then that's actually another cool piece of it. You can record once you find a signal that you're interested in, you go to those narrow bands, you're recording all of that data. And you can say, oh, I missed this blip that I just saw over here on the waterfall. I'll flip back over, and you can replay it back in time. That part is the part where as soon as I saw that, I was like, that would have been amazing, because I know some people probably have some high-speed HF radios where you can record the voice. But think about re-recording or recording the entire IQ data in a stream where you can go back and say, oh, this person was, this is a contester and I missed his call. I could go back in time and I missed it because I was on the wrong modulation, whatever. I can go back and remodulate it and listen to that call sign. So that part kind of blew me away as well, aside from the fact that this actually works, which was kind of amazing to me. All right, so it's low cost. This is low cost to the government. So I'll be honest here, for a person's not going to buy this typically on their own unless they have like some really interesting use case scenario. The system's probably about 100,000, I guess, if I were to kind of pitch it that way. But for the government, for the purpose of what this is doing, it's pretty low cost as far as, this is one of those systems you can put out in the field, and if it breaks down, you're able to take the main components and then send it for repairs, and it's not going to be a big loss. It's not like losing like a $1 billion airplane or something like that. So okay, so this is just another picture of it. We have the vertical whips up here, and then we have in the middle is the air grid. So it's just a ubiquity radio, and so that can transmit back to a computer that can sit there and do processing and understand what's going on with figure out what signal they want to tune on it. Is basically what it is. Okay, and it's all solar, which is super cool, because then you can it stays running. I think when we ran this a couple times, and so here we go, perfect, NTC. So the first use, so after I tested this thing out, and the first thing I did is I did what most of you guys would probably do as well, is fire it up and DF WWV. And as I said before, if you know the angle of arrival and the elevation of arrival, there's one more missing component you can figure out that you need, is going to be the elevation at which the signal refracts off the ionosphere. So you need to know that as well. What I've always done with this system is well, first I looked up the F1 and F2 layers, trying to figure out exactly about where they're at based off the time of day. That works really well. But the easier way is actually just tune in WWV, and you basically move the location of where the signal is coming from to Fort Collins, and that'll give you an estimate of where it's bouncing off, because it's doing its DF, and that's a known location. So that's literally how I calibrate it when I do it in the United States. From Nepal, I think we did it off of WWV Hawaii. Or another known signal is how you would do it. But so we took this thing to the National Training Center. If nobody knows what that is literally like, if you want to deploy in the United States, that's a place to go. It is it's a rugged terrain. It's like being in the desert. It is, I think it's the Mojave Desert is where it's at. So what we did is our challenge was basically that center picture, which is Tifert Mountain. About 3,000 feet above the surrounding terrain. If you have somebody doing VHF on one side of the mountain and somebody doing VHF on the other side of the mountain, those people are not going to be able to talk. We proved that directly by doing that. And oddly enough, there's kind of like a hill right before it, if you could barely see it. I don't know if you can see my mouse, but right in the before that, it's a funny story. We sent someone over there and we could talk VHF. And I was like, oh, was like, you're on the other side of that first hill. Like, how could we talk VHF? And I think it was weeks later, Don and I were discussing one of the ham tests, and it talks about this thing called knife edge diffraction. And the concept of that is you're still going to get a bit of bleed over that can bounce back down a hill if it's not high enough, which is that knife edge, and it's not going to be much, but it could be enough to make it work. And that's when we realized that was what was happening when we were there. We were getting knife edge diffraction on that first hill. And when they drove around to the other side of the mountain, there was no VHF comms. Like, that was definitely not working. So we did the as scientists, just saying, okay, let's make the most optimal way to make this work. Well, we had a buddy poll, and as I was doing research on Mars frequencies and what frequencies would be best for the time of day, it turns out that 5.25 megahertz was like an operating frequency for Mars, and something we could use. I didn't want to go through the there's different ways to do it. We could have done the frequency manager through NTC, but this was an easier way. And so once I had that frequency, I realized the buddy pole doesn't do 60 meters. So I went to a website actually in Pennsylvania, and they were doing a bunch of NVIS comms, and they've set up buddy poles and on different configurations. And I think it's in the buddy pole manual now, but it actually showed us how to just add some wire and basically extend the dipole of a buddy pole out. And so we built that antenna, extended it out, did some quick tuning, and it worked beautifully. We were doing JS8, which was kind of new at the time. I know it's kind of been around a few years now. We did some JS8 because our whole goal was we wanted to be able to talk more than everybody's here's probably done some FT8. FT8's very awesome. It's a great protocol. One of the most advanced, ham protocols we have. However, it's very scripted, and you can't send a text message. So what we wanted to do is be able to send a text message, which is what Jordan Shear did with the JS8 call. So we did it. We set that up, and we had the Watchdog going on at the same time. We were looking at the elevation of arrival, and it was like 85 degrees, and we were receiving the signal. So we were basically doing the application of NVIS for the purpose that we wanted to do. Our whole goal was, how do you communicate when that mountain's in the way and you can't talk to VHF and you have no satellite comms? And JS8 proved to be something that was more fantastic than I ever thought it would be. And I think, okay, so this is kind of a Google Earth view of what we were doing. So we had our transceiver 1. I think I was actually where transceiver 1 is. Transceiver 2, position 1 and position 2, they started off at that one position, then they moved to the other position, and T-Fort Mountains are right in the middle there. We tried VHF on both times, literally just to verify that there was no weird ground wave path that could happen, and it definitely did not work. And then we used HF. So what I did, I'm a computer scientist, so I like to visualize things and understand like what is actually going on. And this one I built this probably in the hotel room after we were done, like a day later. And I was trying to understand how high is the ionosphere. And I don't think that we always think about that when we talk on the radio. We're just happy when we can make that DX contact. And so I plotted it, and then I extended up based off the ionosphere for that day. And what you see here is the signal's going, like I said, 85-degree angles. So on the left-hand side, it's going straight up, and on the right-hand side is coming straight down. And this slide here shows about where it would be bouncing off of. Now, this is not like a propagation model. This is literally points in Google Earth. So it's not like I modeled this with like some kind of exquisite software. All I did is say that the top point is where the ionosphere is, and the bottom 2 points is where we were making a contact. And I can verify that at 85 degrees on one end, we were receiving that signal. But it gives you a bit of perspective of you are bouncing the signal straight up off the ionosphere and coming right back down. But the thing I think that's fascinating is the magnitude of what we're doing, because we're sending a very low power signal up this high just to go across this very short distance. but radio waves like direct line paths. And so it worked. And that part I think was really cool. Let's see. Okay, I should have reviewed these slides again. I've mixed these up a little bit from what I've done before. Okay, so yeah, this shows the Watchdog doesn't have the best GUI. It's more of a scientific kind of GUI. It's not an Army system that's like that's out there as like a program of record. And so we're still working to kind of get there with that. But this is in the middle kind of, or that top one is showing what we're looking at. And it can also do some really cool stuff with beamforming to try to null out signal noise from other sources that are away from where you're going. So yeah, this was 331 degrees and 85.8 degrees elevation coming in. On the right-hand side is literally what the system looked like when we set it up. That is the system that received the signal. And then the bottom left, that's when we were setting it up. And the bottom right, I think we were just operating it remotely, just showing that we could do that. Okay. So let's see what else I have. Oh, so this is where we're going to do with the Watchdog. So the last thing I would say, and I don't have this really in the slides. So when we did this, one of the things I thought that was important is, I know some of you have operated FT8, you probably leave your radio on at 100 watts, or if you have an amplifier, maybe 500 or whatever. The really cool thing about JS8 or FT8 as we were doing it is we kept bumping down the power. And I know we're supposed to do that as ham operators, but I don't think we always really take that into account. And so what we did is we our whole goal is if you don't have satellite comms and you're being jammed, you should probably also try not to produce the least amount of power as possible. So we want to know what would be the least amount to make this work. We bumped it down to 50 watts. We could do NVIS voice at 50 watts. We were using Elecraft radios. I don't have pictures of that right here, but the Elecraft KX3 is what we had. So we could do 50 watts, no problem with the voice. As soon as we went below that, it started to become harder to understand. So we switched to the digital mode. Once we switched to digital mode, it was working fine at like 25, then 10 watts, then 5 watts, and then 1 watt. And again, I think about this when I think about 1 watt. That's a long distance to go. I think it's I don't know, 200 kilometers, I think. So that's a really far distance to go with 1 watt. Then we dropped it down to 500 milliwatts. At that point, it was really hard for the Watchdog to even pick up the signal. When we went to 100 milliwatts is when that's when my mind changed about how things work, because at 100 milliwatts, we were still able to 100% copy the signal, but the Watchdog actually couldn't DF it anymore because the signal was just so far in the noise. So that's a data point I think that's kind of the most important from this part of the presentation. But for ham operators to kind of bend this, again, this presentation I've given to is a kind of a multitude of different ones, but I think you ought to surprise yourself. Pull down your power on your radio and see if your FT8 is still working, because you may find that you really don't, if you have a good antenna, you may not need a whole lot of power to go a very long distance is really the thing that I think is interesting. Here's where we hope to put these. We had one in Afghanistan, we pulled it back during COVID. Okay. Yeah, so I know many of you probably know all of this, but I think that it's important to just look back at the history of all this. I mean, Packet, AX25, we still use APRS. I talked to Bob Berninga about a year and a half ago, I think, who does the whole APRS piece, which is AX25 based. So that's READY was developed in the Navy. Phase Shift King, some of you probably use now. ALE is what the military likes to use. I'm kind of mixing up a few things here because ALE is not a modulation. It does use MFSK, I think, is the modulation based off the standard. Unfortunately, the commercial world likes to implement it their own specific way. The standard isn't good enough to really make it compatible. I don't think that's written well enough to make it compatible between vendors, which is unfortunate. But then again, as I got to ACI in 2017, that's when FT8 was released, and I started using it right away, and I was just so impressed with. And unfortunately, I've not had a good conversation. I haven't had a chance to talk with Joe Taylor. I've emailed him like once, but I really would love to go to one of his presentations, because that's a brilliant ham who changed the world to me in ham radio with FT8. And I don't know if anybody's, probably some of you have gone on. Even if you haven't done FT8, just tune into 14074 any time of day, and you'll figure out how the band condition is. Because if nobody's talking, somebody's talking on FT8. Like it is a constant out there. And then JS8 came shortly after. All right, it looks like this in the waterfall for those who haven't done it. All right, so here's the next thing I love, the reverse beacon network. There's so much research being done on this. I love this because even if you don't know if your radio is working and nobody's talking to you, you can send out a signal, and there's likely a reverse beacon somewhere that's going to be able to report back to you. So if you haven't been to PSK Reporter and done a little digital mode, I would highly recommend you kind of play with this stuff. It is super, super cool. You get on, you could do PSK, you could do different ones. FT8 is probably the easier one once you understand how it works. But once you play with it, you can literally just, you can play with your antenna, you can transmit, you can see who received you, you can mess with your antenna again, or your tuner, or your radio, or your power, and you can go back and see what happened differently. I mean, there's no better science experiment than the reverse beacon network. That's the most brilliant thing. And all it is other people running FT8 or running FLDigi, one of those type programs, that when they receive signals, even if nobody's operating, it'll report it back in, and then it goes to a database that you can look at. So very, very cool way to monitor propagation. I'm sure some of you are probably super avid people, and some of you may have never seen this before. I have no idea, but I would say that if you've never seen it, you should check it out. It is one of the coolest things. I mean, again, I'm a computer scientist, so I'm a little bent on the digital modes here, but I had no idea that HF digital would become something so cool because of the internet. Like I was, when the internet started becoming like a thing, I was like, wow, once cell phones come out and the internet comes out, what's the purpose of ham radio? There's a lot of people speculating, 15 years ago about this. And realistically, it's technologies that can embrace each other. And that's the cool thing about this is we're now in an age where the digital part of our network can actually report on what our HF network is doing. I mean, how cool is that? It's just amazing to me to see how we kind of come full circle. And the internet is not killing ham radio. It's only enhancing it, in my opinion. Okay. So our more recent research was this ethics system. And the idea behind this is to measure the ionosphere. I mentioned before, I'd love to just brute force it and say, well, we know where WWV is, and we can kind of speculate where the ionosphere is based off of our signal bouncing back off of that. Well, realistically, to be more accurate, it's good to measure the ionosphere depending on the region that you're in. And so this system was developed at Penn State for a different program. And we have a couple of these, and basically they do a Barker code, which is a cool way of mathematically setting up a code and figuring out the time of arrival when it comes straight back down. And this is what I was saying before, you can bounce signals straight up and back down again. And that will give you measurements of the F1 and F2 layers. And you can also figure out, I'm not an ionospheric expert, but I listen to them enough where I'm starting to get the jargon right. But there's some nuances of how the ionosphere works. There's things called traveling ionospheric disturbances that come through. And this system, when set up in Pennsylvania, was actually able to detect some of those as they happen, and spurious things that the sun does that cause our ionosphere to change. So with a couple of different sounders, you can actually do some basic DFing as well. So this combined with the Watchdog is something that we've been looking at. If we want to try to find like a hard target that's operating HF, this is actually kind of the way we would do it from a scientific standpoint. Now, I can't get into anything else beyond that as far as how this could be employed. What is it? It's basically, a lot of it's off the shelf. It's EDIS, the E110 SDR is an old SDR. It was built, in the, maybe about 8 or 9 years ago. We're looking at potentially upgrading it. It's got a 100-watt amplifier. I actually want to test this thing out without the amplifier, because I think that people love to put power on things and not understanding, do they actually need it? I'm interested in low power ionospheric sensing, which is kind of one of my things that I'm just interested in doing. So where are we at? We have 6 of these. There are 2 receive channels, a phase coherent. So it basically has a transmit and receive. The dipoles are generally configured the way you see them, where they're perpendicular to each other. And it sends this 13-bit Barker code. And if you look that up, it's kind of like where FT8 is, where it looks at a special type of coding to try to understand where the start and end is. There's a great presentation at the ham site that discussed some of the encoding of FT8, and it's also fascinating as well. But cool, smart mathematicians figure out how that works, and then when we employ those codings algorithms, you get some really accurate systems with this. All right, so that's kind of the system there. If someone's interested in this, you can go to the live site. This is not our system. Our system's on the left-hand side, but I like to look at this because it's something that's, I think, is curious. We modeled it as well. It's kind of like, if we go back to the beginning of my slides, you start to get that absorption, which is happening on the far left of these graphs, and then it starts to bounce off, and then it kind of does a weird like S type thing, and then eventually it starts to penetrate through. So you always kind of have this like upward refraction that happens in the ionosphere. I think it's just interesting to know how that works. There's a dip that always happens too, and that part I can't really explain, but it's because we're going up in frequency as we go left to right here. But if you're interested in looking at the ionosphere, on field day or whatever's coming up, it's worth taking a quick look at what they have going on at the Wallops Island. And there's a couple digisounds that are doing these constantly and monitoring the ionosphere. It could be helpful to tell you, is your equipment bad, or is it really the ionosphere is acting up, or they're just frequencies that are just not usable. You can figure out some of those from here. Okay. This is our goal, is to try to make a network in New York. So we have Rock Springs, which is at PSU, and then ACI where we're at, Benet Labs, AFRL, and Lewis, New York. That's our goal, to put these out. We have one in Lewis right now. We have one at ACI, and we have one at PSU. I've not gotten one to Benet or that's Air Force Research Labs yet. COVID totally dorked up this plan, but it's still potentially going to happen. I have some other, we have to come up with a more robust plan and personnel. There's always resource challenges with doing these things. Okay, so shoot, we're almost at 8 o'clock. That's all that I have for NVIS and those kind of communications. If anyone has any questions, we could go into that. I also have a small presentation here on underground comms, which we did about a year or 2 ago, playing around with trying to understand how you communicate underground, which is a completely different aspect, but also deals with radio.
Phil, I've got a question on your ALE. What kind of antenna do you use for the ALE?
Oh, great question. So for Army people, you use the best antenna you can get. There's the PRC 160 has an incredible antenna tuner. It comes with a whip antenna. We have used the Army antennas are actually not all that. Some of the ones that I've messed with are not all that great. There is the one that we used that was really successful for us it was basically just a dipole, to tell you the truth. We strung up like a very long dipole, and that worked pretty well. But
a single frequency dipole.
No, so the way this dipole worked is it was coiled, so you basically string it out to the frequency. I think it had markers on it, so you string it out to the frequency, kind of what you want. But you're right. If you get, this is something I'm very interested in trying to understand. The longer the antenna you get, you start to get more wideband type properties. The best antenna that I've seen We use actually an Aussie antenna in our last thing in Nepal, or even in Papua New Guinea, I think. And it was a folded dipole. It's a very long folded dipole. We have one at West Point in the Ham Radio Club as well. And that one's a multi-band dipole. And how that works is, I haven't done the modeling on it. All I know is that it looks, I wish I could, I'd have to look it up online and like what the civilian equivalent of it is in DX engineering or something like that. But if you look up like a folded dipole, it can work on those different bands. And what I get what you're getting at with this question. What the Harris radio does is it remembers, once it does it tunes to each frequency, and it remembers that tuning. So as soon as it switches between ALE modes when it's about to transmit, it knows exactly what the settings are to tune it to that. So the antenna tuner's tuned for that antenna that it's on.
Okay.
So
I mean, the reason I'm asking, we're using the Motorola Micom 3 with ALE, and I'm using a B&W antenna for CAP.
Okay,
B&W folded dipole.
Yeah. So no, folded. You might be right. That might be the best way. Everything that I keep playing with and seeing, that seems to be the way to go.
Because you're shifting frequency, and unless you have multiple dipoles.
You're absolutely correct. In fact, I've been thinking about getting one for my house because it seems that the one that we have we have one strung at Bartlett Hall before we got our tower put up, and that thing an antenna tuner will find a way to tune that thing on so many frequencies. It just works really well. So absolutely, no, that's probably the way to go.
Thank you.
Question.
Yep.
Okay, I've been doing FT8 for the last 6 months, being locked in my apartment. And
Okay.
so, we have an extremely high noise problem here. So HF voice is completely out. But I put up, and I have to work stealth as well, because this is a co-op, and nobody wants to know from my radio.
Yep.
So I've been using first I was using an 8TS 120 antenna, and I got quite with a Yaesu 991A, and I was getting, I got quite a number of countries using that scheme, and I got close to 50 countries in about 3 months with less than 100 watts. So then I thought, well, okay, I just can't get these. The thing I can't get is Rhode Island. So what angle I've got this, screwdriver Tar Heel antenna. What angle should I be running off my balcony, so I could get to Rhode Island from Stamford, from Greenwich or Stamford?
I would say that if you could set up, trying to think of your setup, but yeah, a dipole is really ideal. But if you can't do a dipole, you could take a vertical and just put it on its side in a sense.
That's easy to do. I can put it on its side. I'll be kind of half buried in my balcony, but I don't like going over the edge too much, except at night.
No, I would tell you that, that's the thing that, it was Dave Fiedler. That's the name that I was missing at the beginning of this. Dave Fiedler showed this, and he has diagrams in these books that explain how you just take your vertical antenna and bend it and wrap it to the bumper of the Humvee, and you can do NVIS that way. And it's the physics supports this, so it makes sense. You think of radiation, it always comes perpendicular from the wire of the antenna. So if you're trying to go up and back down again, you want your power to hit as directly above you as possible on the ionosphere. And my graph there did not really show what the actual propagation is, because most likely it was more like a big donut or something like that, where it kind of goes up and like funnels back down, or maybe a water or I don't know. I actually would have to go back and look to see
So
exactly.
you would be like like there would be a ring at a certain distance from your launch point that would be the most favorable points to reach.
Right. Yeah. Something like that, I think. But yeah, I would definitely recommend, um, at a minimum, I don't know how that antenna could work if you could bend it at all, but at a minimum you could bend it. But I would say
I can just, rotate it up and down on the
rotate it down, and please let me know, like email Steve or myself if you could let me know if that works. Like if it works and we solve that problem tonight, that's super cool. Like I'd be excited. So, but yeah, I would say, I definitely recommend doing that. And you could use PSK Reporter to see if you're getting there, just in case nobody's actually operating the time that you're operating. But that should do it. Don and I were trying to do, we did between me, I'm in, I think it's about an hour drive, but by the crow's distance is probably what, 40 something miles or so.
Yeah.
When we talked to HF one time, the last time we talked, we were just like, oh, what would be the best frequency? We brute forced it because I didn't want to go on vocap. It was like a Sunday afternoon, and we sat there and I was able to talk to him easily on 80 meters, and it was just that it was perfect conditions, and I had a NVIS antenna kind of set up in the backyard, and we were able to talk. It was perfect. So yeah, if you're doing vertical, that's great for DX, but it's not so good for
yeah,
trying to reach
it's
locally.
Steve, it's 50 miles from my house to yours, from
Okay.
Connecticut to where you are.
Yeah, I can only run up to through 40 meters with my current element unless I want to. I do have some extensions I could try, but they're kind of like hang halfway to the next building. They're like, I got a 10-foot retractable antenna here. It's like
Yeah.
crazy. It's like crazy. Yeah. Crazy
Well,
long.
you could start to do weird things like get an antenna tuner and try to tune a rain gutter. I mean, there's all kinds of crazy stuff.
Yeah,
You can do, but with that, you need to understand your balance and stuff. And I know a guy that's an expert in that. I'm not at all. Yeah, I would definitely recommend trying out turning it on its side. That's a start, and then looking on PSK Reporter and seeing kind of like how that's faring out for you.
Yeah,
But
good idea. That should be fun.
yeah, definitely, very cool.
Yeah.
Awesome.
And another thing I noticed, I was working on Python programming and PyVisa to communicate with a test instrument, and then I noticed if my transmitter was on, I was picking up the 2 USB channels going into the ASU, because it was all tied into the same computer. I work at home, and that probably gives you an easy hack into that. If there's a list of codes for that machine, give an easy hack into the Yaesu. I mean, everyone else is writing soft code for those machines, right? Ham radio Deluxe, they all know the codes.
Yeah. Yeah, and it's unfortunate that I feel like, and I've talked to Don about this, but I have solar panels on my house, and there's just like the amount of noise that messes up my HF is kind of terrible. But
yeah, there was an article in QST a few years back about that problem.
Yeah, and I feel like the newer technologies like solar panels is one thing, but USB is also another thing, which is not necessarily a new technology, but I really miss the old school RS-232 serial ports, because they were much more immune to RF than the USB is. And so I'm glad that the radio manufacturers are starting to build in USB ports so that they can filter it and they can do what they need to do, because I have a Kenwood TS4, is it a 480? I can't remember the number of it, but it's the portable Kenwood one, HF radio, and I think it's a 480 SAT. And if I don't have a bunch of ferrite, maybe it's 440. I can't remember. But well, I have two. So I have the old 440, and then I think the 480 is the newer one, if I remember right. Yeah, when I plug in the serial port to it, if I have a USB converter and I don't have enough ferrite chokes on there, the USB converter just totally blows out when I start transmitting. So that's a whole nother piece that
Yeah, I've got chokes on I've got chokes on everything.
Yeah, definitely. Okay.
Thank you.
Yep.
Great
Any other questions?
presentation.
Yeah, thanks. Okay, if anyone's interested, we could start doing the underground, or I don't know how long your meetings normally last, or it's up to you.
How long is the underground? Because we have to do the, talk about field day yet still, so.
Oh, you got field day. Okay. Well, I could do it real quick, or I could come back another time and do some underground stuff. I haven't looked at this. Let me just look real quick. 1, 2, 3. Oh, it's real quick. I could do it in like 2 or 3 minutes.
Okay.
Please.
Okay. So so this is a problem that we were facing before of what do you do? Underground communications is its own weird issue, right? Because GPS doesn't work and a lot of stuff doesn't go through rock. HF does kind of go through it. So the first thing we did is, how do we communicate underground if you're in a cave-like system? And the first thing we tried was we used the broadband hamnet. I don't know if anybody's here has used it before, but it's I think it's kind of archaic now. I don't know if it's going to be used much anymore. Ubiquity's come out with some pretty good firmware, but basically we flashed the Ubiquity software hardware with the hamnet mesh network. Several years ago, this became like a big thing in Maryland. It's not very good here because because of the mountains, but the idea was you flash this firmware. If you haven't been to broadband hamnet, you flash this firmware on there and you could basically build like a high-speed internet network in your town just using VHF. That was the idea, like 2.4 gigahertz. So we flashed it and we tried this out. We mounted them on like PA tripods and put them in the cave. And basically every point you turn, you drop one, and it's a mesh network, and it worked awesome. Like it worked really, really well. What we did test was what we tested was 2.4 gigahertz, and then we tested 900 megahertz, and we tested 5 gigahertz, and 2.4 worked probably the best in the cave. Then we said, well, if we can talk in the cave, how do we talk to the cave, through the cave, or through the earth to the cave? And so we did some research, and some of you probably heard about the Thai Cave Rescue. The Hayphone, I think, was used in the Thai Cave Rescue, if I remember right, which was developed by Ham Operator. This is like VLF type stuff, so it's really, really low frequency. The other thing is the Nicola Cave Radio, which is the British Cave Rescue Association uses. And I could not get one of those. Like I wanted to buy one from them, and you couldn't really do it. They kind of made them for their cave rescue, and they didn't really do anything else outside of that. So what we first did is said, well, let's use what we have and understand what radios we have and what we could possibly accomplish with our own equipment. So we used the Elecraft. There's a KX3 there. We did 160 meters, so 1.6 megahertz. I'm sitting up here on top here with the of this cave, about 60 feet of limestone, and then you have this other antenna, which is it's literally laying on concrete, and it says they're 1.875 megahertz. Perfect voice. It was perfect. It did perfectly fine. So our idea was, if you have somebody outside the cave, you have people in the cave, you build a mesh network in the cave, and then you have an HF radio outside the cave. And we mocked this up just to try to figure out how this would work. This is just some pictures of doing that. We have a Ubiquity radio. The vertical is the Alpha Delta, I think it's what it's called, the Alpha Delta radio, or Alpha radio, I guess, or Alpha antenna, I'm sorry, with the cool matching unit. So we kind of played around with it. went into the cave. So that's me on the right, Don is on the left, and then the 4 guys in the center are part of our group that all of them have actually left our organization since then. One's retired, and the other 2 are the 3 are doing good stuff in the Army. So what we did is we figured out, let's take a signal link, hook it up to a laptop, hook up the HF radio, and it looks kind of crazy, but basically our whole goal was we did a voice over IP call through a mesh network in the cave, connected it to the signal link, which connected to this HF link, which was a 1.87 megahertz through the earth. So we basically proved that you could go voice into a cave and then basically have a phone call made through the cave. So if somebody was way deep in the cave, the mesh network would get you in the cave, and the through the earth would get you through the earth to get to that entry point. So that was kind of the experiment we did, and yeah, that was it. It was super cool. We did try all different frequencies. Definitely the lower frequencies worked a whole lot better. 7 megahertz did not, 40 meters, it didn't work. And then anything above that didn't work. In the cave, 10 meters didn't work beyond one of those like big pedestals you see of the limestone. So it got kind of blocked. So you really need the very high frequency in the cave, and you need the very low frequency to go through the earth. So that was basically, I mean, something that you could figure out, but we tested it and actually did it, which was a lot of fun. And I think after this, the last thing that we did, which is not in these slides, is we did buy these CanaryCom radios, which we have now. And so we have 2 of them at the ACI, which operate at it's like, I don't know, 600 kilohertz or something. It's really, no, it's 60 kilohertz. I'm sorry. It's really, really low. It's wave in the VLF, I think, range. And I have, I'm hoping this summer we're going to get some ROTC cadets to do some testing with that. And ideally, we're going to bring that out to a cave. And we want to see how much rock you could penetrate with super, super low frequencies. So that's that's kind of our next thing of looking at, what we can do with this. And it's not necessarily for a particular mission. It's just so that we can put on the books, yeah, if we're trying to operate in these weird conditions, this is what we would need to operate with. So that's it. That is my last slide. So any other questions? Any questions about the subterranean communications? I know that's not really a ham thing, but it's funny because it seemed to be like a ham solution helped us kind of get to where we needed to be, which was really fun.
Steve, thanks. This is Don. Really appreciate your talk tonight. Thank you so much.
Cool.
Yes, thank you. Any questions on Through the Rock? Come on, Stan.
Okay. For your NVIS antennas, how high is your dipole? How many, is it a 1 wavelength or half a wavelength, or what do you normally do?
That is a fantastic question, and I'm gonna answer in a couple components. So first of all, you do what you need to do for your mission. So you do what's easy to do first. If it doesn't work, then you try to figure it out. Ideally, I believe by the math, it works out to be a half wavelength above the ground. I think that's the ideal. That being said, I do know an NVIS expert, and I would say he's an expert because his PhD is literally in NVIS technology. His name's Ben Windvliet, and he's in Norway. And I asked him this question. I said, well, what is the purpose of figuring out the distance between the ground? And if there is a purpose for that, could we put like a reflector on the ground to enhance the ability to transmit straight up? Because that's what I was really focused on. And he gave me a very interesting answer. He's like, yeah, you don't really want to do that. He said, if you're starting to get to the point where you want to focus energy, you're going to start using multiple antennas, which was kind of something I didn't really think about. I think he might have been, at that time, he might have been talking more about reception. I could be wrong. or not. But I think he felt like having multiple antennas was going to be a better solution than, now that I say it, it sounds stupid. Like I don't understand exactly why that made sense. Because I was almost thinking realistically in my mind, what would a Yagi look like? You know, like a HF Yagi that's pointing straight up. But I think that, I mean, if you have the ability to adjust the height, I believe halfway the wavelength it makes the most sense, because then you're able to reflect off of the actual ground. It does depend on like the soil content that you're around, but you're not going to change that. So ideally, the half wavelength is where you want to go. But I've done quarter and we've done less. We've done inverted V's, and they still work pretty well.
How about radials?
Thank you.
How about using radials?
Yeah, so you don't need radials on dipoles. If you're doing verticals, you do need the radials. So yeah, so that was kind of my thought, is like, what's the version of a radial for a dipole? Well, I mean, there's no real radial, because literally one part of the dipole is the ground, and so you don't, yeah, it doesn't, I don't know. It's a good question, but I would say that the radials only seem to be, that's kind of like the counterpoise. That's the part that you already have built into the dipole antenna. So I can't give the good physics. I wish I had I have a real smart cadet who could probably explain this a little bit better than I can, but dipoles don't have radials inherently, because the fact that one of the poles literally is kind of like acting as the radial that you would have on an inverted V. So the inverted V, your radials are connected to the ground, which I know I've read many anecdotal things saying if you have a vertical, then you want to have as many radials as possible. You know, you basically want the ground to be like a tin foil or something like that. But with the dipole, the radiation works differently, because you have one of your components of the dipole is the ground itself.
All right, you mentioned receiving now. So you'll be transmitting on one antenna, and so you use something like a beverage or an on-the-ground loop antenna for receiving.
Yeah, for receiving, so I'm on board. The reason why I mentioned that is because when he said multiple antennas, it made a lot of sense to me, because I was trying to figure, I think when he said that, I was like, okay, if I'm receiving a NVIS signal and it's not strong enough, having multiple dipoles that I could feed in would give me a better receive. The Watchdog itself does this, because you literally are receiving the signal from multiple sources, and you can start doing beamforming and doing some really cool stuff to bring up that signal. As far as transmitting, I can't say. I would say that I have no idea of how you would transmit and have multiple antennas transmit the same signal and keep those synchronized enough where it would give you a benefit. So that's the part I probably need to go back to Ben and ask that question, because that's excellent. Like I got focused on the receive side of like trying to figure out how you pick up a weak NVIS signal, but on the transmit side, I think my personal opinion is you're probably still going to be limited to one antenna that you want to have at the correct height, which would probably be a half wavelength.
I've always been intrigued by phased arrays. I don't have any place to put it, but I envision that somebody should be building a transmitter that would allow, I mean, I'm talking at the ham level. I'm probably, the Army must have phased array transmitters for VHF somewhere. But, for a ham station to provide, say, multiple power amps or signals that can come out of your black box there, with varying phases that you might select so you could steer your beam. I think that would be the coolest thing ever.
Yeah, no, you're right. No, and there's definitely research being done and trying to figure out those kind of optimal things. And I'm particularly interested in trying to understand, because if you consider the concept of someone trying to find your signal, you don't want your signal to go anywhere except for where the intended recipient is. And so doing things like phased arrays, doing things like beamforming are super important, because you're trying, you know, when you transmit, it's like a light bulb. I mean, a light bulb is a transmitter of a very, very high frequency, right? So I always like to think of it that way, to rebase, understand what I'm trying to, what we're trying to do here. But you light up the sky when you transmit. And in the Army, we don't like to, in certain circumstances, don't want to tell everybody where we're at.
No.
All right. Thank you, Steve. Really appreciate it.
Thanks for having me
You're
on.
welcome back anytime to partake of the meeting and join us. Like I said, thank you very much.
Okay, cool. Yeah, no, thanks for having me on. This was a lot of fun. And great questions. You got some really sharp people. I wish I could I wish I could to do this all day long. Unfortunately, I I do more admin. Don knows now. I probably do more admin than I get to talk about like cool stuff like this.
We
You're
all
always welcome back to
appreciate
do
your
another one.
Yeah, thanks.
thank you very
Really
much.
appreciate it.
Okay,
Thank
cool.